Okay. Lecture 19. Oh. It seems like we have a delay in the response time of this system. So, well, anyway, let's just start. Lecture 19. Okay. So, the title of my lecture in this semester is actually subtitle is DTCO, Design Technology Co-Optimization. So it's now think about the overall landscape of this design technology co-optimization. So I'm not saying that this is the overview of the entire activities about DTCO, but I want to say that this is more related with TCAD centric view of this model. Many different researchers are saying they are doing DTCO. I'm doing DTCO and you are doing DTCO. So one example is if you are a circuit designer, even in that case, if you are doing some jobs in routing, so how can we connect our contacts with the metal lines? And they say that I'm doing the DTCO. And also another process engineers, and they are saying that I'm doing the design technology co-optimization by changing something. So there are many different flavors of this DTCO, but I want to say that this is more related with the TCAD centric view. Let me just think about this one. Here we have many different subdomains of DTC or activities, but the main root of this routine is first we consider certain device. Actually, is this really the real fabricated device or the device in our mind? So, depending on that one, we can also make different categories. But anyway, we have a certain device. After that, we have two different routes, one for device and one for metal interconnect. So for device, we can predict its performance and we can make here, this is not covered in our lecture up to now. So from this device characteristics, then we can make a simplified model to specify IV characteristics of that device or CV characteristics of that device. This is usually called as a compact model. And also we have another route here, and this is more related with backend of line stack. So what is backend of line? We have not covered it yet, but it is related with the metal interconnect and their relative capacitance. And from this given backend of line, then we can extract resistance and capacitance, and this one is also used. So in circuit simulation, maybe you have heard about SPICE. So in a SPICE simulation, we need certain models for devices and backend of line in metal interconnects. These are entered into this SPICE as input parameters. After that, we do something. Yes, we can make a certain simulation and say that is this meeting our criterion for performance or not. If it does meet, it's okay, then we are happy and stop the loop. However, in many cases, it's not. Then we must improve the performance. So what we do is, from this one, this is not that much automatic. So just to observe the, how can I say, the performance, and after that, engineers, these are humans, these engineers make some idea to improve the design. This is the role of creative role of engineers. And after that, then what will happen? So intuition is not sufficient to optimize this entire system, because although we have some strong belief that this new idea potentially improve the situation, but nobody actually knows. So this DTCO once again start with this new idea for our layout technology or the different knobs. Then we started this job once again with a different layout. Then now we have a different structure, and that is repeated until we have sufficiently good enough performance. So in that case, we have to calibrate our tools. So let's think about this one. If our generated structure is far from the realistic structure, then even though we can perform very accurate calculation and very accurate modeling of our compact model or parameter extraction, everything will be just incorrect. So think about this one. We have someone, and our goal is make this guy very beautiful. However, he or she is our customer, and we can provide, for example, a hat or very beautiful clothes, shoes, or teach the way to attract other persons. We can do many things. However, let's think about this one. Instead of this guy, actual customer is this guy. Then what will happen? Our strategy will be just complete failure. So as the beginning of our DTCO framework, first of all, we have to make the reasonably good structure for our realistic structure. So that's the reason why we need to perform this long series of process emulation. And once after we have a good enough, accurate enough structure, then now we have to perform the device simulation to extract intrinsic parameters, intrinsic devices parameters, and this BOL extraction. But more or less, this parameter extraction for metal interconnect is given. Their sizes are much larger than intrinsic device, and its physics are also relatively simple. So people think that in this route, this is a matter of computation. Once we have sufficient computational power, then extraction itself does not introduce much error in our extracted part. So only the problem is the system is really huge. So if we consider standard libraries, then there are several devices and they are interconnected quite a complicated manner. So we have to solve a very large system with several devices. That is the problem. How can we speed up this entire parameter extraction part? That is a kind of a critical problem for this route. And sometimes we can get quite much advantages of advanced numerical techniques. So I heard that from my friends that by introducing clever idea, so they were able, he and his team were able to speed up this parameter extraction part by orders of magnitude compared with the commercially available tools. So how can that happen? Um, yes, because they are clever, but anyway, we have some knobs or some rooms to improvement. But more or less, the physics are known here, and we can just perform this extraction job. Another one is more related with intrinsic device. Intrinsic device means that the device we are currently talking about, FinFET, CFET, nanosheet MOSFET, those kind of intrinsic device has some feature size several 10 nanometer, and which is much smaller than this metal interconnect. And point is, inside it we have a much complicated device physics than metal interconnect. So now you understand what happens in the intrinsic device. In order to make a switching on and switch off, we usually rely on the inversion phenomena. And in order to do inversion phenomena efficiently, we have to have a very clean interface and suitable work function and very high channel mobility, and also we have to have a relatively low resistance for contacts. They are all important and they are all quite much cross correlated. So therefore this part is more governed by advanced physics, and that is relatively difficult. So for that purpose we need additional tools listed here, and these are just calibration tools for our main tool here. So this tool is used as our main tool only because it is fast. It is not accurate, not that much accurate. However, compared with these calibrating tools, it's much sorry, much faster. So that's the reason why we are using this tool every day. So advanced transport solvers are being used as calibration tools. Once calibrated, as shown here, so as shown here, then we just make extensive use of this tool. And how many hours do we need to take the IV characteristics from this given structure? It is typically orders of hours. So hours means that depending on your structure size, it can be several minutes and it can be several hours. So minutes and hours to humans, it makes a big difference. So if it takes several hours, sometimes it is like related to night. We have day and night, and we must sleep. Engineers, every engineer must sleep, and there is a certain time to stop their creative job. So therefore, in practice, the time limitation for our everyday use of this tool is just given by overnight. The longest time duration you can have is before leaving your office. You start your job, and when you come back to your office in the morning usually, then you can have your simulated job done properly. So therefore it is orders of several, about 12 or a little bit longer. So that is, there is a time limitation. If that exceeds that number, then you have to wait 2 days, 3 days. So therefore, of course, in reality, so engineers, if that is really important, they can wait several days or even several weeks. But you cannot perform that kind of heavy jobs every day. So you have to find out champion job, which is critically important for your achievement, and just submit it and wait for a long time and get some information out of it. So many cases, this is just a daily job, so hours or overnight. Then now you have IV characteristics of usually for one single device or a family of devices. So for example, we are currently working on inverter example. In this inverter example, we have multiple pins here and there. These are MOSFETs and PMOSFETs, and they are connected. That is regarded as a relatively large size system. So because we are more or less, in many cases, when we perform this kind of device simulation, we focus on just a single device performance. So simply speaking, even though we have different fins, but what we do usually just to consider one fin for MOSFET and one fin for PMOSFET and simulate them individually, separately. So then now we have single fin performance for MOSFET, single fin performance for PMOSFET, and say that, oh, there are 3 copies of these identical fins, and also there are 3 fins of this identical fin. So by combining them, we can make the entire inverter system. When that is allowed it, or that is possible, then we are quite happy. So here we have, for example, 9 persons, but if we can just analyze this group of 9 persons as the sum of individual motion. I move, you move, the other guy moves. When we just collect them all, then we will quite happy because we can concentrate on movement of each person. However, let's think about this one. We are now interacting. I'm teaching and you are listening and doing some job, and your motion make another influence on me. So if we are interacting to each other, then can you make the clear cut between you and me? This current situation cannot be made simplified. So important point is, in this case, what is important interaction and what is relatively less important interaction. That is the key point. If I were allowed to analyze this system once again, then I would like to, everybody in this room can make interaction, but in this case, most important interaction is I, or instructor, and individual students. So think about this one. We have several students in this room, and here instructor, and they can interact to each other. So everybody and equally can interact to each other. However, if we are clever enough, then what we can do is, okay, among different interconnections, maybe the most dominant ones are the actions like this one, and relatively less important one is the interaction between our students. So are you talking to each other, or are you looking at me? So maybe in this system, when we analyze this inverter system, then we must select what is the effect we will see from now on. If they are really separated, then we are fully allowed to analyze individual ones. So, and previously, in our previous technologies with the planar MOSFET, it was allowed to perform individually analyze each device. However, nowadays, even, for example, even FinFET, we have different devices. Their interconnection mainly comes from the source and drain. So let me just explain. From the top view, we can have one fin and another fin and also another fin. Of course, they are shared by, so here we have a diamond and also diamond in its source and drain, and here we have a diamond. So please try to imagine what is the three-dimensional view of our system. And of course we have running gate. This is gate and source and drain. If we have this situation, then previously we were allowed to consider only, for example, one single fin. It was because our metal comes from somewhere and laid on top of it. So therefore, of course, depending on the position of each fin, this fin and another fin and another fin can interact, but their interaction can be relatively small. But now think about different device called as nanosheet MOSFET. Then it is actually in this FinFET, then this is X direction in our usual coordinate, Y direction, and now this is Z direction. That was the FinFET layout. However, now what we have is X direction and Z direction. In this vertical sense, now we have here and there one stack, another stack, and another stacks are here, and they are also connected by certain source and drain. This is source and drain, and this is a silicon channel, and silicon channel. My question is, previously when we had FinFET, even in that case, we were worried about maybe they can interact to each other, especially in terms of their contact resistance. However, now when we have a nanosheet MOSFET, it is really clear that they are interacting. Where can you find the source and drain contact? Here we have a source and drain contact, and here we have a source and drain contact. They are sharing the same starting point of their electron injection or hole injection, and now they are competing to each other. For example, now electrons are injected, and if this guy have a much lower resistance, then current will be dominated by this top root. However, now think about three different stacks are equally resistive. Even in this case, we have an interaction between them, because starting from this source contact, the access resistance to the entrance of this slab or this stack, and this stack and another stack, which one shows the highest resistance and which one shows the lowest resistance? You can easily understand this path is shortest, and we have lowest resistance. And here we have a long distance, and although we are trying to improve its resistance as much as possible, but still it is resistive. So simply speaking, even when we apply same gate voltage to this top stack, middle stack, and bottom stack, still bottom stack does not conduct as high as this top stack. So that's the reason why, by applying this philosophy, then we can actually increase the number of stacks quite easily. Here I just drawn 3 different stacks, but we can make a 4 stack, 5 stacks. So even, for example, if we attend some international conferences and some research groups showing 8 stack devices, yes, they have a really huge amount of own current. However, if we just draw their own current as a function of stacks, then that does not improve any longer. I mean that if we have 4 stack and 5 stack, of course 5 stack device will perform better. However, if we go to 6 stack, yes, 6 stack will be better, but improvement between 4 stack and 5 stack, there was delta, and from 5 to 6, of course there will be another delta prime, but delta is always larger than delta prime. Our improvement is now diminishing, and yes, that's the reason why people believe that in real process, in real fabricated silicon devices, maybe 4 stack or 5, I don't know, but 4 stack will be the maybe practical limiting value for stacks. So in this case, I wanted to ask you once again, so now in this system, can we perform the device simulation only for this top stack and say that, okay, this one represents these 3 different stacks, and using this single stack performance, I wanted to just predict the device performance. It's not possible because they are getting some advantages of lower access resistance. So the problem is, the trend is, now we wanted to integrate more and more devices into small area. So therefore, in order to reduce area, many things are integrated in a vertical direction, not in X direction, not in Y direction, but this Z directional integration becomes more and more popular. So they are accessed from top or bottom, and we have to consider this G directional structure quite accurately. So now the amount of or the size of system in its X, Y, and also Z direction is increasing. So that's the reason why we must consider ever increasing larger size of a system here. So anyway, that was the device simulation. Once after we have this working spend several hours, what we get is simply spend several hours. What we get is simply this IV characteristics, ID versus VG, or ID versus VD. These curves are obtained, and but in our actual chip, we have billions of transistors. Then single device takes several hours. Then how can we simulate billion transistors? It is almost impossible. So okay, I will not, of course, I will not try to simulate the entire system. I will just a small piece of circuit. However, even in that case, the number of transistors is not several tens. several hundreds. So there still can be thousands, even millions. It is really easy to increase the amount of transistors. So it is not feasible to perform every time to this device simulation. For larger system, we need to more efficient way to describe the behavior of our devices. So that's the reason why we have now compact model. And compact model, what is compact model? Simply speaking, it is more elaborated version of this expression. So I'm a little bit exaggerating, but roughly speaking, what is a compact model? So it is like the model collection of terminal current expressions. So when you apply gate voltage, then you can get drain terminal current. So of course the life is not that easy even for this compact model. Actually this is a very complicated and sophisticated field. However, basic principle is once you give me the combination of terminal voltages, then I can provide you quite accurate and calibrated drain current, gate current, and source current, substrate current. That is also not just current, but also I can provide capacitance. That is the role of a compact model. So once we have IV characteristics, then that should be matched to existing compact model. Or since our course is more and less ticket centric, I'm saying that this IV characteristics is obtained from ticket simulation. But if you are working in industry, then your IV characteristics is no longer coming from ticket tools. They are really measured and you have the real data. Then when you have the real data, then that is matched to your compact model. So once this one is over, then now you have a well calibrated intrinsic device model and also well extracted parasitic RC components, and you can perform also quite a reliable simulation for your circuit. Then you can trust the simulated result, and based upon this simulated result, you can also reiterate this scheme. Once again, if we have the real silicon data, then that should be done with the real silicon data. However, even in that case, we have a limitation, time and resource. In order to make this kind of a procedure in real fab, it takes months for making this one. So even fabrication without any design, even fabrication itself takes about, in its shortest time, 3 months. So if you have a new idea about something, then in order to really observe that effect in its measured data, you need at least 3 months. And how about this design? It takes another time to perform this kind of job. So even though the real verification or real silicon data is ultimately required, however, before doing that tedious and time-consuming job, we must do it much quickly with these TCAD tools. That is the main use of TCAD tools in industry. Then you can improve the performance. Oh, well, the reason why we are using these tools is our improvement target is so tight. So tight means that in this field, 1% difference of performance is regarded as a significant improvement. If it is orders of 0.1%, then maybe they feel that, oh, there can be a different effect. So it is regarded as less significant. But if one change in our technology knob introduce about 1% difference in its performance, then they feel that, the engineers feel that, oh, something happens, and that is a really important improvement. So that's the reason why, compared with the other engineering part, so in this case, the accurate evaluation is really important. So we do not expect orders of magnitude improvement for something that can be achieved when you change the entire architecture, or when you just entirely change your channel material. Maybe you can expect that significant amount of change, but usually in your lifetime, maybe that would or would not happen once. So even for my lifetime, there has been no change in the channel material. So, and well, if you ask me, do I expect that change once in my lifetime? I'm not that sure. So therefore, that is really huge change. So in reality, we are very severe competition with competing companies in technology development. So every technology node, this 1% difference is really huge impact, and we are really stick to improvement and accuracy. Okay, we must think about that one. So please do not underestimate the importance of a 1% difference. We must really be careful. And now I spent quite a long time to discuss about what is the overall ticket-centric DTCO, and we have covered up to now these two tools, process emulator, so generating the realistic structure. And today we will talk about how can we use drift diffusion simulator. Of course, we have already spent 2 previous lecture slots to discuss about drift diffusion model. However, that was done for planar MOSFET, so relatively old time device. But today we wanted to do just to connect these two tools. So once we generate the device structure, then we wanted to send it to the device simulator. And once we have this capability, when you change your device structure, then it will eventually affect the performance of your IV characteristics, your device. So now once you have this loop, then even with these two tools, you can make iteration. So for example, how much can I reduce the channel length? Then if you reduce the channel length again and again, then eventually you will have a severe short channel effect. Of course, even without this process emulator, we can perform that kind of assessment. So you can just draw it and simulate. However, that is not as realistic as the one generated by this process emulator, and processes are quite much complicated. So that's the reason why we are trying to connect them, avoiding just the heuristic drawing tools. So how can you couple these two tools? So they must share a device structure file. This guy, process emulator, generate a certain device file. It was named as a something.cgns. This is a common file format, and we are using that file format. But once after just Armstrong craft code is over, now we have a certain structure file, but that structure file just to describe the surface of this structure. Simply speaking, although it shows a certain fin fat, yes, now say that this is a fin. So our Armstrong craft provide this beautiful shape for our fin. Then the information it has right now is only this surface information. And how about something inside it? Intentionally, it avoids specify that part, because if we specify this volumetric information, then amount of information gets too high. So for efficient implementation, we do not care about this volumetric information intentionally. However, now when we go to this drift diffusion simulator, now we have to have certain physical quantity as function of position. This is position and this is a physical quantity. So we need to consider the internal structure of our device simulation domain. So that's the reason why now we introduce a new capability developed by Mr. Minse Jang, sitting over there, and he is contributing this one. Actually, although I'm the author of Armstrong craft code, so for today's lecture, I have no idea what happens. So I'm just showing his example file. So let me just have a look at his example file. Today's lecture, I will show you some simplified procedure to make a certain three-dimensional structure, but that is not my main point. Once after we have simple device out of Armstrong craft, after that we will just convert it to another device structure suitable for device simulation. That conversion, file conversion, is the important one we will discuss in this course, today's lecture. Okay, so since it's a fabrication procedure is quite much simplified, I will just quickly discuss about this one. Here we have a silicon and silicon germanium stack. So here we have a blue one. So first of all, sorry about the colors. Colors are matched perfectly. Sometimes meaning of colors are changing one picture and another picture, because you know that is just related with the appearance of each region. So now this blue one is silicon, and this green one in this figure, that is corresponding to silicon germanium. And maybe you remember that the very first example we have considered in our Armstrong craft exercise was that silicon germanium stack. So although we have just a single silicon layer, however, in reality we have multiple layers. The number of this silicon stack really determines the number of channels or stacks. So if we have just a single silicon layer, then this is a single stack, but in reality we have three stacks in the most advanced technologies. And it is true that for a while we will use 3-stack devices. So I'm not sure when we eventually move to 4-stack devices. Well, it's not that clear. So the reason why we consider just a single stack is to simplify our exercise. Well, anyway, the thickness of this silicon layer is said to be 5 nanometer, and since we do not consider any kind of etching, additional etching for this silicon layer, the final thickness is also 5 nanometer. That is the result, but I'm not quite sure. So in reality, we must consider eventually a small loss due to etching process, but we consider this probability. Silicon and silicon germanium has perfect separation in its etching rate. When you try to etch silicon, then we can perfectly etch away only silicon. And when we try to etch silicon germanium exclusively, then also it is possible. That is assumed. And in reality, we have quite a good selectivity, higher than 10 to the 1. So higher than 10 to 1, that selectivity is achievable with a certain germanium contents, but still we have to consider a slight loss of a silicon channel, but we do not consider that here, and that is shown here. And also there is one limitation in current implementation. If I remember correctly, then here the numbers are multiples of 4. Oh, why 4? Because 4 is 4 is a power of 2. So it means that, well, if you are considering do your own job, then please try to set your domain in multiples of number 4. Well, so I really wanted to make this 127. Okay, but even though you wanted to do that, please just add one more to make 128 to make it multiple of number 4. Yes, now we have this one, and actually, although this is a nanosheet MOSFET, you will find that the procedure for fabricating this nanosheet is quite close to that of FinFET. First, fin formation. And in this fin formation, fin width is set as 12 nanometer. This 12 nanometer is kind of a little bit narrow value. Even we allow wider values like 19 nanometer for very scaled devices. So 12 nanometer is a somewhat scaled value. So it means that 19 nanometer line with much larger distance or larger pitch, about 60 nanometer scale, that is really makes our life easier than FinFET. Please remember our ASAP7 case. It was fin pitch was 27 nanometer, and fin itself was just 7 nanometer thick. So it was really difficult to make it. We had to apply quadruple lithography. So, however, now in this case, now we have the pitch longer than 60 nanometer, and in this case, fin is in realistic case about 20 nanometer. It is much easier to draw them, so that is good for this nanosheet case. Of course, since we are using much wider space, then how can we match the effective width? That is compensated by introducing multiple stacks. That is the key idea to compensate the use of a wider area. So we are using wider area, but instead of that, not just one stack, we intentionally introduce 3 stacks, so it can be just regarded as 90-degree rotated fins in some sense. Previously we had fins in vertical direction, but they are just rotated 90 degree to match effective width. So now we have I can just quickly skip this part. So now we have patterning, fin patterning and STI. Yes, this is now STI, but now after that dummy gate. Yes, this is dummy gate, and after that this is spacer, and now this source and drain. Here we have a source and drain, and here we have a source and drain. They are etched away. After that we grow source drain with epitaxial growth. However, this part is the most important difference between FinFET and nanosheet MOSFET. Here we have some structure called as inner spacers. So that's a shape is not that clear because we are currently using just one single stacks, but think about multiple stacks. Now we have multiple stacks made of silicon, and silicon, and here and to be more okay. So now here now we have a silicon germanium and silicon germanium. So silicon, okay, so let me just draw in this way. Now we have a silicon germanium, and also we have made this this one is spacer. However, this one is called as outer spacer. If we do not make the inner spacer formation is, can you see clearly here? We have a small part, small portion of previous silicon germanium intentionally etched away. So underneath this outer spacer region. So now we intentionally make this spacer silicon germanium much narrower. I mean that here, this one also. Now we make this kind of we make this kind of thing. After that, we will add another spacer material to fill this etched part here. It is because eventually we will remove this silicon germanium entirely. So what will happen? Now this silicon germanium will be eliminated. After that we will make our gate on this part. So gate will be filled in this part. So problem is, let's assume that we do not make any kind of this inner spacer. then what will happen? This part and this part will be covered by our gate formation. However, quite nearby here, we have source and we have drain. So it means that isolation between source and gate and isolation between drain and gate is not available without this inner spacer. That is the key difference between this nanosheet MOSFET and previous FinFET. In the case of a FinFET, we just used the entire silicon and there was no silicon germanium. So therefore we don't have to introduce any kind of structure called as inner spacer. However, in the case of nanosheet MOSFET, we intentionally introduce silicon and silicon germanium, and eventually silicon germaniums are removed. So we need to make another one, because when we initially make this spacer called as outer spacer, usually just a spacer, then the part for silicon germanium is already occupied by silicon germanium, so we cannot make spacer for that part. So without inner spacer, we cannot isolate gate and other terminals. So that is I will explain a little bit further later. So after that, now we have etched some portion of silicon germanium, and how deep is this inner spacer etching? That is really important, because you know that introduce the distance between source and gate and distance between gate and drain. That is determined by this difference. Its control is important. And how can you generate this distance? Just etching our silicon germanium. And how much we can etch silicon germanium precisely? For example, we wanted to etch it 7 nanometer, but due to process variation, let's say that we just have 6 nanometer etched silicon germanium or 8 nanometer etched silicon germanium. That will make a huge difference between the capacitance between gate and source and gate and drain. So it is really important to control the inner spacer etch. After that, in reality, we grow here the source drain epitaxy. So in reality, since this is the shape of our fin, usually what we have is from the frontal side of this nanosheet, now we have a certain diameter shapes. So they are expanding, and also they are expanding. So if we wait for a while, then usually what we have is starting from this one. Now usually we have this kind of shape. Previously we had a fin, and starting from this point we had certain lines. So that's the reason why we had this diamond. In the FinFET case, our starting point was this one, so eventually we have the shape like this. However, in the case of our nanosheet MOSFET, it is a combination of fin, and on top of it we have also this nano sheet. And important point is the shape of this nano sheet. So now we have a certain shape. Oh, sorry. And this one also grow, but this fin is not as how can I say, as tall as the previous fin. This one is really used as a channel material. However, this fin is not used as a channel material. This is just covered by STI and another, eventually another dielectric. So we will not actually want to use this one. So the use of this fin is only because we wanted to eventually connect this one and this one eventually by selective epitaxial growth, and we wanted to apply the stress from this deep substrate. So once they are connected and this channel can feel the stress coming from this substrate, so that is the way we wanted to apply the additional stress for our nanosheet. But anyway, so in reality we have to consider the accurate shape of our source and drain. But in this simple example, we just feel without considering a detailed shape, but I think that it's completely okay to demonstrate the conversion from Ångström Craft file to the G-Device file. And after that, we have this one is a salicide, and another one is, now you can see that colors are changed, but this is still spacer. And now we have, previously we had dummy gate, but this dummy gate is eliminated. Now we have, so they are the same one, I just rotate it to see it. Even though dummy gate is etched away, now still we have silicon, germanium, and silicon, germanium. So we don't want to have this silicon germanium. So even this silicon germanium should be etched away. So that is performed, and that is called as usually channel release. Channel was overlapped and hidden by silicon germanium. Silicon channel was sandwiched by silicon germanium layers, sacrificial layers, and eventually these silicon germanium layers are gone, and now channel is released to the air. So that happens here. You can see that this is the silicon channel now released. Then the point is, can you see it clearly here? This one and this one. These two are inner spacers. So it means that if we don't introduce this inner spacer, then the place for this inner spacer will be also etched away, and now our source and drain is just exposed from this route and this route, from this channel region, gate to B gate region. So we have a direct connection into source and also to this drain. So we must isolate them. That's the reason why we must introduce an inner spacer. And precise control over inner spacer is really critically important. Let me give you one episode I have actually seen in the last year IDM. In the last year IDM 2024, I guess, TSMC successfully announced that they have developed their 2 nanometer technology. And they said that they presented a very beautiful thing. And there was one question, of course there were several questions, but one question from a certain person, do you use inner spacers? That was the actual question asked by one audience. Then the answer was TSMC engineer just to say that yes, we are using inner spacers. Why that happened? It was because there is also another company who can fabricate this nanosheet MOSFET, and they really suffer from the control of inner spacer. So eventually they gave up and make another process, another device technology without inner spacer and distributing it to their customers. Then what will happen? Although DC performance can be achieved, but their AC performance is really bad. Because if we don't have inner spacer, then gate and source and drain are so tightly coupled, so we cannot operate them sufficiently enough. But that really happened in last year. Exactly 1 year ago, I have seen that Q&A session, and another engineer complained that, our companies are struggling from fabricating inner spacers. And what happens? Eventually, they realized that inner spacers are mandatory, and they tried and wanted to introduce inner spacer back. So that is really important to have inner spacers. And inner spacer itself, the concept is simple. However, controlling that thickness, how can we precisely control the amount of silicon germanium matching? That is the critical thing we have to consider. So that is nothing related with our computation. So in fabrication side, we should be able to control accurately. After that, high K metal gate will be added. So that is not that realistic, but I think that it's okay. So up to now, we have done a similar job with the FinFETs, and now we have a single stacked nanosheet MOSFETs. Although this is much simplified, but the general procedure are not that much different. Then what's the next step? We wanted to simulate it. So for that purpose, Mr. Minse Chang introduced a new capability in the Armstrong craft. Now it has a mesh command, and this is exemplified. That is really a long line. There are many lines, but I can just skip many of them. So where can you find these files? So you can find it in our GitHub repository. So I will just introduce it and wrap up today's lecture. So now you have a subdirectory named as a single step, and now you have 3 different ones. This is structure.cmd. That is just containing the procedure we have seen up to now. So by performing the Armstrong craft with this structure.cmd file, you can have simplified single stack nanosheet. After that, when you learn once again another Armstrong craft with this mesh.cmd, then now you can generate the same device but internal mesh point. So simply speaking, when you go to this direction, then this is the output structure, the resultant structure of meshing. So previously, when you visualize the previous structure, you had just a tall cuboids, because tall cuboids are basic building block of Armstrong craft. But now you can see that there are many cubes in here, and actually the size of cubes are different. So that is the way we make the efficiency. Actually, I didn't make it, so he made it. So once again, thank you. Without your help, we cannot make this semester's lecture available. Oh, so you can see that here we have a substrate, and substrate is not that important for our simulation because substrate do not conduct. In this case, we introduce a quite coarse grid. And which one is the most important one? Here we have a stack, the single stack. This one is divided with a very fine grid. And here we have a source and drain. Yes, I think that he introduced a relatively coarse grid than this silicon stack, but it is finer than substrate. What is the controlling parameter for this resolution? So here you can see this number, resolution 2202. This is used to control the size. If you say resolution equal to 0, that is the maximal resolution. So maximal resolution to us is right now 1 nanometer. 1 nanometer, 1 nanometer, 1 nanometer cube is used for this part. And if you introduce 1, it means that we are now trying to introduce 2 nanometer spacing for this region. And 2, it means that we are trying to make a 4 nanometer long spacing for our structure. That's the reason why our structure should be multiples of number 4. So okay, anyway, good job. Then let's come back. Now we have a volumetric mesh, and using that one we can just simulate it. Then now you are looking at the result of our example file mos.cmd. So now you can have it, but this one is just performed without any mobility model, and the number shown here is too high. So this is really overestimated. So please try to add physical models and try to get reasonable result than this one. And my final advice is, when you learn this Armstrong craft.mesh.cmd, then you will have the intermediate input file for G device. This one automatically generated this memmaker.cmd file, and you must learn once again this G device memmaker.cmd. So maybe it would be much better to make this procedure a single shot, but right now what we have to do is first generate the structure in Armstrong craft and run the meshing file, mesh.cmd file, but it does not provide directly a CGNS file. Instead, as its output, it generates mapmaker.cmd file, and this one calls, using this one we just run mapmaker file, then internally it generates its own mapmaker routine and generate complicated structure. So what we do is to teach this mapmaker routine, how can you draw some complicated structure without manually specifying its complicated structure. So I think that right now you may have many questions about what is the exact meaning of these all lines. First of all, here we have region specification and contact and related with this context, and also doping. But frankly speaking, I have no idea about what are they. So I will study this one, and maybe next lecture I will give you another more concrete explanation about their meanings. So now you have homework number 19. Homework number 19 is so easy. Just take 3 input files given in our GitHub repository and try to learn. However, after you did it, then you will have highly overestimated IV characteristics. Oh, it's not that good. Then please just add physical models and try to rerun with it with physical models, and you will find that actually convergence behavior is not that easy. Sometimes you will have unconverged result. Oh, then how can we avoid that problem? The best one is just to reduce your max step. That is, in many cases, that is the key parameter. If you set max step too high, too large, it means that you allow quite a drastic change in your voltages. But in many cases, that introduces convergence failure. So now, when you include more and more physical models, then usually you are reduced to the small max step values, and it takes quite a long time for you to perform this IV sweep simulation. Okay, do you have any question? So I'm quite sure that some of you will have a failure about learning this program. Then please don't hesitate and do not wait till the last night. So just directly send me an email to ask to improve the situation, because you know this code is not available to anywhere, and nobody except me and other TA and some guys, we cannot fix that problem. So please tell me whenever you have a problem. Okay. Thank you.